Thank you for TechBlick coming here. I'm going to talk about a unique material system for solid-state batteries. So I'm a faculty member here at Yale University. I'm recently moved from University of Maryland here. Um, so so, I'm going to introduce basically what is nanocellulose, how do we make them ion conductor in a solid state, and how do we use them in batteries. Right, so brief introduction about cellulose nanofibers, especially for the battery community, that the so wood is basically is a composite material, right? With with cellulose, with lignin, and with hemicellulose, right? And if you zoom into the wood fiber, that typically has a diameter of 50 to 100 micron. If you zoom in, you will see all these wonderful cellulose nanofibers with a diameter of few nanometers. And so these fibers, nanomaterials, they have amazing mechanical properties. For example, the tensile strength can go all the way up to 7 gigapascal. I think maybe one of the strongest fibers. But at the same time, they have a very weak bond between the fibers. It's a secondary bond. It's about 0.2 eV per bond. But because you have so many of the bonds, so the material made of cellulose in the format of a paper or wood can be actually very strong. So I think all these interesting aspects of this abundant, sustainable material. And our goal for this talk, of course, is how can we take advantage of this nanomaterials, and most importantly, how do we make them as an ion conductor. So I'm going to quickly talk about the two ways of engineer these fibers. So the first one is about the nanoscale engineering. The idea is that you take the fiber, extract the fibers from wood that has a diameter of few nanometers, and then you engineer the space between the fibers, or engineer the chemistry on the surface of the fibers. Then you have this nano ionic channels for batteries. And then second part, I'm quickly talk about that is our innovation, that is really about how do we further open up the molecular scale, chains in the fiber. Now the fiber themselves are ion conductive and in a solid state, right? And then and we use them in batteries. Yeah. So the two major process approaches when we're using the wood nanofibers, right? So the very first one is it's called bottom up. Means you find ways to extract the fibers. You typically mechanically you chemically swirl the fibers, and you treat these fibers, and then you mechanically break them apart or beat them up to these nanofibers. So you have this transparent gel, and you can assemble them into membranes and separators, and in batteries or some other applications like packaging. Right? So I've done a lot of work when I was in Maryland. And the second approach is something called the top-down. Right? So you take the entire wood and you cut them into different size and shape format. Right? You can make a very thin veneer, or you can make a bulk structure. In this case, you open up the nanofibers in the structure through chemical treatment. Then you can have all these aligned fibers that can be very important for ion transport in the membrane. So here we'll focus on the nanofiber space, right? So when the fiber distance is large, more than 100 nanometer and so on, you have a typical bulk, a transfer behavior. You don't have a selectivity, and the space is larger than the solution, the dependent in this case. But if you getting the fibers close, or you open up the space within the fibers in the wood, you start to have this very small channel that is typically less than 10 nanometers. So now in this case, when the ion transport through the channel, it will be influenced by the surface charge as well as the geometry effect of these small narrow channels.